Okay, so we just computed the EIF12. Now, let's see, what did I have there? Gee, I forgot, because I had to do some transitioning, whether I had shown the F11 and the F12. But just in case I didn't, this would be repeated. But anyway, so we have EIF11, which would simply be sketch 1 times sketch 1, right? So it would be minus 2/3 of x squared dx from 0 to L, right? And then plus the integral of minus 1/3 of z squared dz from 0 to 2L, right? And so that is going to give us F11, and it turns out that that proves out to be 12/27. So EI times F11 is 12/27 of L cubed, right? By inspection, we notice that we have the same thing for the F22, and so I'll write them over here. So EI F11 equals EI F22 equals 12/27 of L cubed, right? Now we go to the last step, which is to calculate the delta 1 and the delta 2 on the formulation. Clean it up a little bit. No, that didn't work. Try this. Okay, that's a little better. So now we have to do, let's see, I could erase this one, well maybe not, maybe I can do it here. So here is the primary structure, right? Without the redundance and with the loading. W. This is what we call the P-sketch, right? So we have the x1 equal to 1, the x2 equal to 1, and now the P-sketch. Since this is W and this is 3L, then it's obvious that we have a reaction over here, which is what? 1.5 WL. And then the other side, we also have 1.5 WL, right? Then we take a bubble over here, right? And from that bubble, I think it would be obvious that I will write right away that the MP is going to be 1.5 WL times X, right? This is our X. And in this case it's positive because that is compression on the top, which is what I decided to take as plus, minus WX times X over 2. You can take a look at the bubble. We've done now hundreds of those, so that should be evident that you take this bubble here, have a shear, an axial, and a moment, and the moment would work out to be that. And that works for all X, right? That works for all X. And if we wanted to start from here, by the way, right, we would get that MP is also described by 1.5 WL times Z minus W times Z squared over 2, right? So this is a full expression for the moment. This is also a full expression for the moment. Now, given those, let's see, what can I do without erasing it? I don't seem to have much room to do anything. But maybe, well, I'll erase this because I have them written down and you've already seen them. That'll give me a little bit of room down here to work. Not much, but a little. Okay? So, if we have, let's see, where do I put that other thing? If we have that that expression for our MP, then we can certainly say that EI times delta 1, right, is equal to the integral of what? Of M1 minus 2/3 of x, right? Now that's only good over here, right? X is only good from 0 to L. So that's from 0 to L, correct? Times MP, which is 1.5 WL minus WX squared over 2 dx, right? That took care of this portion of the structure. We've multiplied M1 times MP. For this part of the structure over here, we were going to have plus the integral. Now what can I do? Here, this part, since I have this part here described in terms of z, I'm going to use this equation. So I have from 0 to 2L, M1, which is minus 1/3 of z, multiplied times MP, which is 1.5 WL times z, minus W times z squared. That was wet there. Minus W. Minus WZ squared over 2 dz, right? From 0 to 12. So you carry out that integration and you find that EI delta 1 is equal to minus 11/12 of W L fourth. So it turns out that EI delta 1 is minus 11/12 of W L to the fourth. Okay? That is, you carry out that. I think you would see that if we were to do EI delta 2, we would get exactly the same number, right? Because this sketch and this sketch are really the same thing when you compare it with the multiplication with that. And so we have our process completed, and I can now, I believe, since you've seen this for a while now, I'm going to erase the whole thing, okay? Erase the whole thing. I know the flexibility and I've calculated delta 1 and delta 2. And so let's create some space and put the final steps on it. Okay, so if we write our equations, what we have is, let's see, what do we have? Why didn't I write it? We have L cubed over AI multiplied times 12/7, 12/27, 12/27, 7/18, 7/18, multiplied times the redundants x1 and x2, plus delta 1 and delta 2, which were minus 11/12 of WL, minus 11/12 of WL, equals to 0 and 0. Okay? So those are the two equations with two unknowns, which if you solve for x1 and x2, you get x1 equal to x2 equals to 1.1 WL. And that concludes the problem from the perspective of computing the redundance. Once we have the redundance, we're done, right, in the sense of solving for the indeterminacy, because we now have a determinate problem, if you want, right? Because we know the value of the reactions at the center supports. So recognizing, I think with the time, I'm gonna have to get another one of these things, make it a little bit more efficient. So now let's finally do the statics on the complete problem and draw what we were asked, which was the shear and the moment diagram, right? So here is the beam. Had a support here, right? A support there. And this support here is a 1.1 WL, right? And this support here (1.1 WL). And then there is a uniform load on top of the whole thing, which is WL. So you see, it just now is just a beam, simple beam with two known loads, which happen to be the support reactions necessary to ensure that there is no deformation at that point. Now, summing forces in the y direction, this is 2.2 and we have 3 WL, so the difference is 3 minus 2.2 is 0.8. From symmetry, it follows that this will be 0.4 WL, and this would be, I'm sorry, not down, up, 0.4 WL and 0.4 WL, right? Or you can say some of the moments, you can say anything you want, right? Those are the two reactions on that simple beam. So now we can quickly draw our shear and moment diagrams. So here comes the shear diagram. So the shear here begins at 0.4 WL, right? As you know, it goes down with a slope equal to the applied load. So therefore it goes from 0.4 WL, and a bubble right here just before the reaction is going to have minus WL, so that's going to take us to minus 0.6. And we are here as minus 0.6 WL, right? If we cut on the other side of that reaction, we will find that there is a jump of 1.1 that will take us to 0.5 WL, right? So that's the shear diagram up to there. Then this takes us back again at constant slope to 0.5 WL on this side, right? So we go like this, crosses in the middle, boom, and we have 0.5 WL. And then we have a jump of 1.1, which takes us to 0.6 WL here. And then we go back down at a constant slope of 1, and we cross here, and we have minus 0.4 WL and 0.6 WL. And so that is the shear plot. Okay? This distance from here to here is obviously 40% of the length, right? This one that remains here is 60% of the length. So, how we calculate the moment diagram? Again, we can do it in many different ways, but I'm going to follow, we could go back to our x1 equal to 1 and x2 equal to 1 and just multiply both sketches times 1.1 WL, add them together at the moment of the P load, and we would get the moment diagram. Or we can calculate the moment anywhere we want by taking a bubble at that point and doing statics. Or we can go to the shear diagram and just use our standard procedures of civil engineering of calculating the area under the shear diagram. So how much area is there here? 0.4 times 0.4 divided by 2, that's 0.08 WL squared. Inside that triangle. Inside this triangle is 0.6 times 0.6, which is 0.36. Divided by 2 is 0.18, so that area is 0.18 WL squared. This one here is 0.5 times 0.5, so that's 0.25 divided by 2 would be 0.125 WL squared. And from symmetry, I can see what all the other ones would be, right? So the moment at this pin is 0, and then the moment goes up and peaks here because the shear is 0. So it peaks there like this. Actually, let me be a little more scale next time. So it peaks there like this, right? Then it goes down like this. And the moment here is going to be 0.08 WL squared, right? Which is this area. That's how the moment goes up. The change in the moment is equal to the area under the shear. The slope of the moment is equal to the shear, so the slope here is 0. Moment is 0.08 WL squared. From here to here it changes by minus 0.18. So if we subtract minus 0.18 plus 0.08, we get minus 0.1 WL squared, right? Then here there is another positive moment, and it's going to be minus 0.1 plus 0.125 would be 0.025. So this one here is 0.025 WL squared, and the diagram would be like this. And of course the plot continues completely symmetrical like this, and then here is here, and that goes like that, and then like this, and this would be 0.08 WL squared, and there would be minus 0.1 WL squared, and we have our moment diagram, right, over the complete beam. Now, a number of points which are interesting to note. Notice that, just so that you develop structural feelings, right, feel for structures. Notice that you have a bridge or span, they are exactly equal length, right? This is L, and this is L, over 3 supports. Now, if you say, how big is the maximum positive moment on this span? Positive moment, the one that's bending it down. The maximum positive moment on the edge spans is 0.08 WL squared, right? 0.08. The maximum moment on the center span, even though they're equal length, is 0.025 WL squared. Therefore, the moment in the edge spans positive is more than 3 times the maximum positive moment on the center span. Okay, which you might find surprising at first. The largest moment on the beam, on the 3-span beam, occurs actually on the negative. It's a negative moment occurring under the interior supports. That is 0.1 WL squared, you know, about 15% bigger than the positive moment here. Okay, if this moment, if this beam if I draw it with a size, right? I draw it with a size, and I want to put the supports here so you can see them, like that, right? If that were a concrete beam, then the reinforcement would be placed where? It would be placed where there is tension, because concrete is weak in tension. So in this region here, at this point, the bending is like that, right? Positive. So tension is on the bottom, therefore over here we need reinforcement to protect against, to close any cracks that may form, or the cracks that will form over there, right? Then the moment is positive all the way to here, and so we would need steel, in theory, something like that, right? Then the moment is negative after that, starting here and ending here. And negative moment means that the tension is on the top, and so there would be steel over here, right? And then again, there is positive moment over here, up to this point. And then there is negative moment here again, up to here. And then there is positive moment again, right? Now, in reality, that's not how it gets reinforced. In reality, this steel is prolonged. This steel is prolonged for a number of reasons. This steel is prolonged like that, like this. This steel would be prolonged this way somewhat and somewhat more this way, and the thing would be like this, right? So the rebar reinforcement on that structure would be like that. In essence, these bars would look in a plot as if there was rebar every time all the way down in the bottom, and on top of the supports you would have these negative steel bars, right? That's how the bar would be reinforced for as a reinforced concrete structure. We would, in addition to that, as you will learn in your concrete class, then when you see the shear diagram, these shears produce inclined cracks, because remember, more circle, when you have shear you get inclined tension, and so the shear will require stirrups, and so the stirrups would be things like this that are intended to close diagonal cracks, right? And you can see that the shear is biggest around these supports, so that the stirrups would be closer to each other in the region here near the supports, right? There would probably be stirrups everywhere, but that's what they would be closer. Okay, so I encourage you to pass this exercise that I just did in clean for your notes, and that is not a homework, but I encourage you to pass it in clean, and that you complete all the actual computations. I just gave the final answers to many of the things, EF11, EF12, I showed the integrals, but I didn't do the computation. That you take the opportunity to do the computations and see that you actually get those results. Okay? All right, we'll be communicating soon again. I have been trying to check whether they have announced time for the final, but as far as I can find, nothing yet. So I'll keep checking.